Hello everyone, good evening.
Good evening, sir.
Good evening,
Yeah.
sir.
Okay,
Good evening, sir.
I was a little delayed. Okay.
Good evening, sir.
Yeah, good evening.
Good evening, sir.
So I came to know that, yesterday instructor has discussed the algorithms. Am I right? Like he started with weighted graphs and everything, and
Yes,
he
sir.
does
Yes,
this
sir.
Dijkstra
Singles.
algorithm and Bellman-Ford algorithm,
Yes,
Yeah.
right?
two algorithms were discussed.
Yeah. So two algorithms has been discussed, and he skipped the middle part, which is longest path and transitive closure, and as well as matrix multiplication, right?
Yeah.
So do I have to go through that, or shall we discuss the algorithms? Let's take the poll. So shall we discuss longest path in a graph and transitive closure, matrix multiplication, and everything? Or shall we start discussing Floyd-Warshall algorithms and minimum cost spanning trees? No one would like to say anything, is it?
Sir, actually, I have completed half of week 11 only. That much
Mm-hmm.
I have understand up to week lecture number 5.
Mm-hmm.
And after that, I have not watched the lecture. Up to single source shortage past, I have covered. After that,
Okay.
negative weight, all pair shortage, minimum cost, this part I have not.
Mhm. Okay.
And sir,
So okay,
please
let me.
extend at least
Uh,
time, sir, because we are getting very less for this week only.
mhm. So yeah, I will show the screen. I will share my screen, and I will also highlight the concepts which are there in week 11. So out of this, yesterday we have discussed this Dijkstra and Bellman-Ford, and anyway, you are going to have one more session, solve with us session. In that solve with us session, there are questions on this prims and Kruskals. So we have detailed slides in regards to that. So if you ask me to discuss longest path, transitive closure, matrix multiplication, so I'm asking those guys who are not comfortable with longest path are there any guys who are not comfortable with this terms and
I think, sir,
everything?
briefly discuss them, then it would be better for us.
Okay, I will do one thing then. So let me
Sir, I
start
have
discussing.
also, sir, up to only a 4 point I understand. After that, nothing, sir.
So up to Dijkstra, is it?
Yes, sir. Yes.
Okay.
Yes,
So
sir.
let
And
me
the
do one thing.
Floyd-Warshall and algorithms are a bit confusing.
Okay, let's do one thing then. As you have studied the extra algorithm and Bellman-Ford algorithm yesterday, so let us do Floyd-Warshall algorithm, and then we will come back, and if there is time, we will come back and see what is this longest path, transitive closure, and matrix multiplication. And these concepts are nowhere related to these things. Okay, so you no
Okay,
need to
fine,
worry.
sir.
Okay.
Is there any
So,
book for graph theory? Would like to recommend.
see, graph theory is of two kinds. Okay, so one is electrical kind of graph theory, and one is mathematical graph theory. For mathematical graph theory, I suggest Bondi and Murthy.
Sir, one question I would like to ask: the open session of maths, is it for
Hmm.
doubt solving, or there we discuss all
See,
the
it
parts?
depends. It depends on. See, that is why I asked if everyone is comfortable with the concept, we can directly discuss the problems of practice assignment or activity questions.
No, sir. Actually, up to 20th, we only revised the at least revise for quiz 2. After that, we get time for this.
Hmm.
And at least one day, our time gone for traveling, sir. So
Oh,
that's
so you
that's
got
the
only
thing.
one day to look into the contents, is it?
Yeah,
Yes,
sir.
sir.
One day extension will be enough, sir.
Deadline.
Yes, sir.
Deadline extension. We are looking into it. So we will try to postpone it to
And also, sir.
Saturday or Sunday.
Okay, sir. That
Hmm.
will be great for us, sir.
Hmm. And also.
And these concepts are up to discuss. I understand only.
Hmm.
Yes, sir. And like This longest path are all fine, but this from Floyd-Warshall and Bellman, they are a little bit confusing.
Okay, then we will go directly to Floyd-Warshall. Okay. So let's start with Floyd-Warshall algorithm and try to compute. See, Floyd-Warshall algorithm. See, before that we will see what kind of algorithm to be used for particular situation. Okay. So this is very, very important. So what is the problem statement is in front of you and which algorithm you should use. Okay. Let's briefly see this and then we will skip to Floyd-Warshall algorithm and we will look how to solve the problem using Floyd-Warshall algorithm. Okay, fine. So there are mainly four algorithms, mainly three algorithms. We are not going to discuss Warshall algorithm. The Warshall algorithm is different from Floyd-Warshall algorithm. So that difference you just see it in the lectures. So I just don't want to discuss that Warshall algorithm. And mainly we will be focusing on three algorithms. First one is Dijkstra algorithm. Second is Bellman-Ford algorithm, and third one is Floyd-Warshall algorithm. So let us look into the problem statement and what kind of algorithm can be used. So for suppose the problem statement is to find the shortest path from a fixed source. Source is like starting vertex. Okay. So you have a starting vertex with you and you just wanted to find the shortest path from that particular vertex to every other vertex in the graph. And also that particular graph has only positive weights, non-negative weights. Okay, so that means there are no negative edge weights in the graph. So for this kind of problem, in order to find from single source, single vertex to every other vertex, we can use Dijkstra algorithm or Bellman-Ford algorithm. So both the algorithms you can use. So Dijkstra is the time complexity of Dijkstra is very much less than compared to Bellman-Ford algorithm. So Dijkstra in particular where we use is if you have a single source and single destination vertex, then you can directly use Dijkstra algorithm. So you can directly find the shortest path between two vertices. And also you can use Dijkstra starting from one vertex to every other vertex if you want to find the shortest path. And also if that graph has no negative edge weights, then I can use Dijkstra and Bellman-Ford also. Okay. And the next thing is if I have negative edge weights, then what happens? The same situation. So I wanted to find the shortest path from one fixed source vertex to every other vertex in the graph. But this time the graph has some negative edge weights. Okay, few edges having negative values. But the main condition is there shouldn't be any negative cycles. Okay, my graph shouldn't contain negative cycles. It can have negative edge weights, but it shouldn't contain any negative cycles. So this is the situation we have now. So for this kind of situation, we can only use Bellman-Ford algorithm and Dijkstra cannot be used in this algorithm. So Dijkstra you can only use if and only if your graph has no negative edge weights. That means if your graph is having only non-negative weights, either zeros or positive values, then only you can use Dijkstra. So if you have negative weights, then you have to use Bellman-Ford algorithm. And these two algorithms can only be used from a fixed source vertex to every other vertex. So our source vertex is fixed. And from that source vertex, we are trying to find the shortest path to every other vertex. So what if I don't fix the source vertex? I want between any two vertices, I wanted to compute the shortest path. So for that kind of situation, so if I wanted to find the shortest path from any vertex to any other vertex in the graph, and in this situation, it may or may not have negative edge weights also. So even though if it doesn't have negative edge weights, or it may have negative edge weights, it's fine, but it shouldn't contain any negative cycles. So now the situation is I wanted to find the shortest path from any vertex to any other vertex. Okay, it's not like I am fixing my source vertex. Now my source vertex is different, and my destination vertex is also different. So end vertex is also different. So I wanted to find shortest path between any vertex to any other vertex. And that graph also may or may not have negative edge weights, but definitely it shouldn't have any negative cycles. Then in this kind of situations, we can use Floyd-Warshall algorithms. Okay. So all these algorithms are applicable only if there are no negative cycles. So that you have to very much make sure about that. If you have any negative cycle inside your graph, you cannot use any algorithm. So these are some.
Sir, except this Kestra, everywhere we can use negative vertex, right?
Negative
edge
edge
vertex.
weights. Edge weights, not the vertex weight.
Oh yes, sir. Negative edge weights. Yes.
Okay. So now you see, if the questions are like this, find the shortest path from vertex A to vertex D. What kind of algorithm? So I just wanted, you just have to answer me only which algorithm can be used to solve this particular question. So the question is, you have to find the shortest path from vertex A to vertex D. So in this, if the graph is given like this, which algorithm can I use?
Dijkstra.
Dijkstra.
Sir, but Bellman and Floyd will also work, right?
Yes, sir, that will also work. But this is suitable.
See, but the question is the shortest path from vertex A to vertex D. Okay. So I'm fixing my source vertex, and see, Dijkstra algorithm, time complexity of Dijkstra algorithm is very, very less compared to Bellman-Ford algorithm. Okay. So that is why using Dijkstra will reduce your time to solve this particular problem. So you can also use Bellman-Ford. Okay. But the best thing is to use Dijkstra for this case. If the graph is like this, so what kind of algorithm can I use?
Bellman-Ford.
Bellman-Ford.
Okay, Bellman-Ford. Sure.
Sir, how to see the negative cycle?
That, see, for that, if you have negative edge weights, you try to compute the Bellman-Ford algorithm. You try to solve by taking one vertex and try to find the shortest path to every other vertex using the Bellman-Ford table. Okay. If your graph has some 6 vertices, after the 6th column, if it got converged, maybe you can say the values are constant after the 7th, 8th, 9th columns, all the values are constant. So you know Bellman-Ford algorithm, right?
Yes, sir.
So you will draw a table, right? You will initialize few things, right? So D1, D2, D3, correct? So here there are 6 vertices. So it will go till D6. So compute the shortest D6 values in this column and also compute D7. Okay. So once you compute D7, all the values which you got in D6, if you get the same values, then there are no negative edge cycles. If the value got changed and it is reduced, one of the value got reduced, try to compute D8. Okay. And once you are computing D8, still if it is reducing, it is not getting converging, it is actually changing. If it is actually changing, then there is a chance of having a negative cycle inside your graph. Okay.
Sir, I have one question. Between B and F, the arrows are on both the sides. Then how do you consider which way you can go?
See, from B to F also it is 4, and from F to B is also 4. That is how you should consider.
Okay.
See, it's like there are 2 edges.
You can take either the route from A to B and B to F, or no, and then F to C.
Yeah.
And then C to D.
Yeah. So this is like this. It is given like this. Okay.
Okay.
So,
but the values which we have to calculate, we are adding them, or how do you find?
No. We are not adding it. You just separate it. That's it. So while you are computing
A to B, we have 2.
And A to B you have
B to F it is 4. So 2 plus 4.
4. Yeah, correct. 2
and
plus
then
4.
F to C is 5.
F to C is minus 3. Okay.
Or minus 3.
Okay, minus 3.
C to D is 8.
Okay.
So we have to add it like that, or subtract that minus 3 when we are going from F to C. And the weights are these numbers, right?
So whatever the number you are seeing on the edge, on top of the edge, are the weights of that particular edge.
Okay. And how do you decide which one will be the shortest path, depending on the total of the weights?
No. That is why this algorithm we use these algorithms. So these algorithms will give us the shortest paths. Okay. So you have to understand how to compute these algorithms, how to use these algorithms to compute the shortest paths.
Okay.
Then by using these algorithms, you can actually compute the shortest paths. So that algorithm will give you the shortest path. So by looking at the graph, it will be difficult to find. So that is why these algorithms are useful to find the shortest paths. Okay. Yeah.
When all the numbers are positive, we can use
Dijkstra algorithm. Yeah.
When some of them are minus, we can use Bellman-Ford.
We can use Bellman-Ford. So you have to make sure. See, in this particular graph, tell me which algorithm can I use?
Bellman-Ford.
It has a negative cycle.
It has a negative cycle. So you see this cycle has weight 4 minus 6 plus 1, which is minus 1. So this particular cycle which you are seeing, B, E, F, B. So this cycle has a weight minus
which is negative.
1. Negative. So now I got a negative cycle. So I cannot use any algorithm. So no algorithm can be applicable. So how do I check there is a negative cycle inside my graph is, perform the Bellman-Ford algorithm. So after 6 iterations, I should get all the values I should get converging to some values. It shouldn't change. Those should be fixed. In the 7th iteration or the 8th iteration, if the values are changing, then there is a negative cycle in your graph. So like that, you can identify that if your Bellman-Ford algorithm is not converging, all the values in the column are not converging, if it is changing, then definitely there is a negative cycle. That will imply that there is a negative cycle inside your graph. So you have to identify that negative cycle. Okay, that is how you can identify. For these small graphs, by looking at the graph itself, see, I am talking about the graphs which have some 100 vertices or maybe even more vertices. So by looking at the graph, it will be very, very complicated. So that is why we will perform Bellman-Ford algorithms or any kind of algorithms. And then after 100 iterations, all the values, you will capture all the values and you will look at the 101th iteration. And if the value is changing, so that means there is a cycle, negative cycle inside your graph, which has 100 vertices. So for that cases, algorithm, unless you use algorithm, you cannot find whether there is a negative cycle inside your graph or not. But this 6 vertices and 8 vertices, till 10 vertices is also very small graphs. So you can look at the graph and you can directly identify whether there is a negative cycle inside it or not. Got it? Yes, no?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now let us look at Floyd-Warshall algorithm. And if there is time, we will also try to solve the same problem using Bellman-Ford algorithm. Okay. So Floyd-Warshall algorithm, just now we have seen. So from any vertex to any other vertex, I need the shortest path.
Sir, Floyd is used to find a negative cycle, right? There is present or not, or Bellman.
Both the Floyd-Warshall algorithm and Bellman-Ford algorithm will give you whether will tell you whether there is a negative cycle inside your graph or not. Okay. See these after few iterations. See after these few iterations, the table will also get converged. So all the values inside the table will be constant. If you look at SP7 or something, if your table values are changing again, okay, then there is a negative cycle again.
Okay, we have to construct a table.
Another table, yeah. So I need this. Now look at this is the graph we have, and the vertices of this graph are A, B, C, D, E, F, G. Okay, and also the blue numbers are the weights of each edge. So from B to D, the weight is 3. Okay, so for this you need to understand few things before we start computing the algorithm, using the algorithm. First of all, you need to understand this term, which is SP power k inside the brackets I comma j. So SP power k is nothing but the shortest path. So SP refers to shortest path, and SP is the table, matrix table, which we are going to draw. So there are here we have 1, 2, 3, 4, 5, 6, 7 vertices. So we will be having SP0 to SP6. So this k represents the number of vertices I can use in between to go from vertex I to vertex j. So be comfortable with the notations firstly, then we can use the algorithm. Firstly, this SPK ij represents, so this represents the shortest path from vertex I to vertex j via vertices 0, 1, 2, 3 to k minus 1. Okay, so you can ask me one question like, here the vertices are A, B, C, D, E, F, and here there is a numbering to it. How do I convert this to numbers? So it is very simple. You can assign each number to any of the vertex. So let me start with assigning 0 to this vertex. 1, 2, 3, 4, 5, and 6. Okay, you can assign any number to any alphabet. If in your graph it is given all the vertices are labeled with alphabets, then assign each vertex with 0, 1, 2. You order your vertices. So you may not see, you can also order starting from B. So you can use B, vertex B, assign it to 0, vertex C to some 2, vertex D to again 1, like this. So the ordering you do, the mapping you do to your alphabetical vertices should be constant throughout the algorithm. So that is the only thing you should make sure. So right now I have assigned 0 to A, 1 to B, 2 to C, 3 to D, 4 to E, and 5 like this. So now what we are interested is this SPK, this power K represents. So I can use K minus vertices in between vertex I to vertex J and compute the shortest path among them. Okay. So that means we will see. I will just tell.
Sir, in that in this diagram, we have put A as 0, but C appears to be the place from where most of the arrows are going.
See that you can
and G
see
appears
right.
to be a place where all the arrows are coming.
See, it's fine. Now we are interested to find the shortest path between any vertex to any other vertex. Okay, it's not like there is a fixed source vertex. So start from this vertex or start from that vertex. So you start from any vertex. I will get the shortest path to all other vertices from that particular vertex.
Okay.
likewise I will get from every other vertex also. So it's
Okay.
not like I will only get the shortest paths from vertex A to every other vertex. So I will get shortest path from A to every other vertex, B to every other vertex, C to every other vertices, D
Okay.
to every other vertices, like this.
Mhm.
Okay. So that is why order doesn't matter. So you can label your vertices, but once you label your vertices, keep that labeling throughout the algorithm. So you shouldn't be like after 2 computations you change the values. So for the 2 computations I assign 0 to B, and after 2 tables, for the third table I assign something 2 to B. It shouldn't be like that. So throughout the algorithm you should keep that ordering constant, but however you order doesn't matter. It's your wish to order. Okay. So now SP0 ij means, you see, now I have to use, so k is taking 0. So if k takes 0, I can use vertices via k0, it will be -1. So that means I shouldn't use any of the vertices in between. So I just have to get the shortest path from vertex I to vertex j using 0 vertices in between. So that is what SP0 ij means. So how can I get the shortest path from vertex I to vertex j without using any vertices in between? So what does this mean?
Weight of that edge from I to J.
No, it
So
means
if
graph as such. However,
if there is an edge between I and j, I to j, then the weight of that particular edge will be the value. If there is no edge, so if I is connected like this, I something there and j, so there is no direct connection between I and j. So unless I use one vertex, I cannot travel to j. Yes or no? So I cannot directly go to j without using any vertex.
Yes, sir.
Yes, sir.
So what you have to give is, you have to give infinite to that particular value, particular cell.
Infinite means there is not a single edge, but it may possible there is multiple edge. We will discover later.
We will discover it later. So right now this 0 represents you have to use 0 vertices in between I and j.
Half is 0.
What?
Number of halves.
Number of?
Half is the number of intermediate vertices, no?
Half? You mean 1/2?
Hops.
No,
Hops and HOP.
Array, you are talking about CT terminology.
Yeah.
Yes,
I
sir.
already told you there are two terminologies in graph theory. One is electrical. They will say nodes, halves, and what they call edges, lines. Is it
Edges, not line, I think.
Edges.
edges only? Okay, edges is common between. They call it nodes. Here we call vertices. Okay, so there is quite a bit difference between the terminologies. Okay, let's use our mathematical terms here. Mathematical terms of graph theory. Okay, so you shouldn't use any of the vertices in between. So you have to use 0 vertices in between. Okay, so like if I have to use 0 vertices in between, that means either I should have a direct connection between I and j, or if I doesn't have any direct connection between I and j, then I will assign the value as infinite. And if there is a direct connection, then the value I should take is the weight of that particular edge. So wij refers to weight of edge ij. So if ij belongs to my edge set, then I have to take that particular weight of that particular edge, or else I will assign infinity to that cell. Now, what does this SP1 ij means? So you see SP0 is done. SP1 ij means SP1, just replace 1 in place of k. So that means be the shortest path. So this refers the shortest path from vertex I to j via vertices. When I substitute k is equals to 1, it will be 0. So only vertex 0. So now what does this SP1 table refers to? SP1 of ij refers to? It gives me the shortest paths from I to vertex j via vertex 0. Only vertex 0.
That means
So
K
what
is 1.
that means?
K is 1.
That means a.
So,
Huh,
but
K is
why?
1 in this.
K is 1. K is 1. Okay. So via 0 means here our 0 vertex is nothing but the vertex a. Okay. So now what I will get? What I am computing? I am computing this SP1 ij. This gives me the shortest paths from vertex I to vertex j. Via in between I can use only vertex 0.
Lot of disturbance is coming,
Okay.
sir. Please
Okay. So
switch off all everybody, sir.
yeah. Please everybody please be on mute. Or Rohini, Hrithik.
No, sir, not at my end.
Okay. Okay, fine. Fine, right? So now,
Sir, one question, sir. This ij is it can take any value, any vertex, but here why we are fixing 0, 1, 2?
For order. So in order to see, firstly I have to go through the graph, right? You finish. I will.
Sometime a 0 will not be the intermediate vertex between ij. It can be 3 or 6.
Then you will leave it as it is. You don't worry about that part. You only worry about.
Question. If this is a question that I have to find such ij, which satisfied that intermediate step is 0 and intermediate is 0, 1, 2.
I didn't get. Can you rephrase your question?
Actually, what I said that ij is random, means it can take any value. So it may or may not be that 0 is intermediate. It may be 6 is intermediate, 7 is intermediate.
Okay, yeah.
But sir, here we represent 0 as an intermediate vertex.
I have.
We are on. Just 1 minute. 1 minute. Let me finish. I will just come. See, here we are looking at only 0. Only the vertex which is represented as 0. So here we have represented vertex A as 0, right? So this will be 0, right?
Yes, sir.
I have the table. I just replaced A, B, C, D with 0, 1, 2, everything. Now what I said is my SP1 table. So SP1 table, all the entries in my SP1 table will give me the shortest paths from vertex I to vertex J, which are having intermediate vertex as only 0. See here from 2 to 6 we have intermediate 4. Okay. Correct. From 2 to 6 I have an intermediate vertex which is 4. But I am not worrying about that vertex 4 right now. I am worried about vertex 0 first of all. Then I am worried about vertex 0 and vertex 1. So like this. So I am actually going through graph. Okay. So I will start from one end and I slowly go through the complete graph. So then only I will get the shortest path from any vertex to any other vertex. So I have to go through each and every vertex and I have to look at all the shortest paths around that vertex if that vertex is being involved. Then I will add one more vertex into this. Then I will add one more vertex, like this. Finally, what I will do is I will get all the vertex into the picture.
Okay, sir, I get it.
Okay. So it's like order.
Sir, I have one question. If we want to go from 1 to 2, there is no edge between 1 and 0, because if we have to go through 0, then between 1 and 0 we'll have to write infinite, no?
No, not always, right? If there is a shortest path, if I include 0 into my path, then if my shortest path is being varied, then I will vary my value. or else I will keep it as it is. See, 1 to 2.
1 to 2 we have a direct path.
We have a direct
So
path and the
that we
edge
can
weight is
write
1.
directly as 1, no?
1. So even in the SP1 table also, 1 to 2, it will not change, because 1 to 2, it is not passing through 0. So there is no path from 1 to 0 and 0 to 2. If there is a path, then we will check these two paths, and whichever is shortest, we will replace it with that particular value. If there is no path at all, you no need to worry at all.
Okay.
Okay. So right now you see here SP0. Let's fill SP0 first, and let's talk about SP1 next. So SP0 is basically infinity or the edge weights. Correct? So 0, 0, it's infinite, and some people will write it 0. So it's like, it's a controversial thing, but anyway, we will write infinite. So from 0 to 0, if I can come from 0 to 0 again, then we will change the value, or else right now there is no direct edge between 0 to 0. There is no loop like this. There is no edge. So if there is no direct edge connecting 0 to 0, then we are going to assign it the value to be infinite. And 0 to 1. So is there any edge that is connecting vertex 0 to vertex 1?
No.
No, there is no direct vertex edge.
So this is also infinite. So 0 to 2. So is there any edge that is connecting from 0 to 2?
No.
Yes, sir.
No, sir.
From 0 to 2.
No, 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 no,
No,
no,
sir,
no,
no,
no, no.
No, sir. No, sir.
So this is also infinite. 0 to 3?
No.
No.
No. 0 to 4?
No.
No.
0 to 5?
Yes.
Yes.
Yes, sir.
Yes.
There is
So
one.
0 to 5
Minus
and the edge weight is -1. And
Yeah,
0 to
minus
6? No.
Yes, -1 and 5.
Sir, are you
-1
writing
and-
the weightage of between the two edges?
Yeah, that is what we have to write, right? This is SP0 table.
Okay.
So SP0 table is, if there is an edge, then you just write the edge weight. If there is no edge, then just simply write infinite.
Okay.
So here in SP0, do we have to consider a direct edge, or you can go through any other?
Only the direct edge. No.
Only a direct edge.
SP0 means you shouldn't use any vertices in between.
Okay. Okay.
Okay. 0 vertices you have to use. SP0 refers to you have to use 0 vertices in between. SP1 refers to you can use one vertex in between.
Okay.
So that particular one vertex, we are fixing it in order. Okay. So one vertex means via 0. So SP3, similarly SP3 IJ means 3 means you can use 3 vertices which are 0, 1, 2. Okay. Now I will compute the shortest paths from I to j, any vertex to any vertex via 0, 1, 2. Only 0, 1, 2. I am not worried about 3, 4, 5, 6. Whether 3, 4, 5, 6 are coming in between any of the two vertices or not, I am not worrying. I am only worrying about the vertices which are coming in between any two vertices. Those vertices are 0, 1, 2. So only vertices which are 0, 1, 2, if they are coming in between, then I will look at the shortest path. Okay. So like this, SP7 means I can use 7 vertices which are 0, 1, 2, 3 and so on to 6. So which gives me
also be infinite.
No, SP7 IJ means it will give me using all the vertices in the graph, the shortest path from vertex I to vertex A, which is what we require.
Okay.
So just
so the columns are to be filled in the same way as we are filling the rows.
See, you can fill while you fill the rows itself, columns will automatically fill. See, from this vertex to this vertex. So from 2. So is there a direct edge connecting 0 to 6? No.
No.
So that is
No,
why.
sir.
So SP0, okay, just understand SP0 means there you shouldn't use any vertex in between. That means there is a direct, if there is a direct connection between two vertices, then the weight of that edge will be the value. If there is no direct connection, then the weight, value will be infinite.
Sir, if these infinite values remain the same till SP7 matrix, it means that there is no reachability from 0 to 4 or 0 to 6.
Correct.
So, sir, this SP0 matrix will have only one row?
SP0 matrix will have only one
please
row.
allow him to teach first, then you ask questions.
Yeah. Let me complete.
Let him finish, then you ask questions. In that, whatever he has taught you, in that any doubt is there, please ask. Don't jump the guns, please. Please maintain.
Okay. See, now I is 0 and J I have varied. So this is I is 0. From 0 to 0, there is no direct edge. So I have given infinite. So I is 0 and J is 1. So if there is a direct edge between 0 to 1, then I would have given some value, but there is no direct edge between 0 to 1. So that is why infinite. So like this, from 0 to every other vertex, I have looked if there is any direct edges. So there is only one direct edge between 0 to 5, which is this edge, and that weight of that edge is -1. So that is why the shortest path from 0 to 5 is -1, and other else are infinite. Now my I will change. Now my I is 1 now. Okay, so let's go to the second row. Now my I will be 1. So I have to look at shortest path from I to J. Now J is 0. So 1 to 0. So from vertex 1 to vertex 0, if there is a direct edge, then I will give some value. If there is no direct edge, then I will give infinite. So from 1 to 0, there is no edge. So that is why it will be infinite. So why I am looking at direct edges? Because this is SP0 table. So SP0 table, you can correlate with adjacency matrix. Okay, there your entries are 0, 1, but here your entries will be infinity or the edge weights. Okay, so now from 1 to 1, so this will be infinite only because there is no edge that is connecting from 1 to 1. So from 1 to 2.
Yes, sir. 1. Wait,
1.
So there is an edge.
Yes, there is
an edge. So that
Sir,
is,
all these algorithms we can use for both directed and both directed and undirected graphs, right?
See, undirected graphs, how can you, if there is a negative weight for an undirected graph?
No, if there is just an edge from 1 to 2 or 2 to 1, it will be same, right? The adjacency matrix will be symmetric, right? Then also we can use this algorithms, right, to find the shortest paths.
Okay, then also you can use, but see, my question is, you can use that when your edge weights are all positive.
Okay, why not when negative?
Why not when negative, you tell me. So what do we mean by undirected?
There is no fixed direction. Is it because we will not be able to identify negative cycles?
No, it's a negative cycle, right? If it is undirected, let's say there is an undirected edge with weight -4.
Okay.
So what does this mean? If I go from A to B, my weight is -4.
Okay.
Correct? And once if I return back, my weight is -8.
Okay.
And
okay.
if I travel again to B, my weight is -12. It's basically, it becomes a cycle again, negative cycle.
Okay, I understand. Yes, sir.
So that is why if you are looking at undirected graphs, then definitely all your weight should be positive.
Yes,
In
sir.
order
Yes,
to
sir.
use this.
I got it.
Okay, let's come back and let's see. Let's fill this table. So I'm going slowly because this understanding this table and filling the values will be difficult. So SP0, SP1, we will go very slowly. From SP2, we will increase our pace. Okay. So we have to fill it. So now in order to fill this particular entry, which is 1-3 entry, 1-3 entry, for that 1-3 entry, I have to look from if there is a direct edge from 1 to 3.
3.
So is there a direct edge from 1 to 3?
Yes.
Yes, sir.
Yes. And the weight of, so if there is, if the answer is yes, then we have to enter. So we have to weight of the edge. We have to enter the weight of the edge, which is 3. And 1 to 4?
Yes, sir. 4.
Yes, sir.
1 to 4 also there is an edge, direct edge, and the weight of that edge is 4. So 4. 1 to 5?
No.
No. So 1 to 5 there is no direct edge. So infinite. 1 to 6?
No.
No.
So now you see from 2. So from 2, now my I becomes 2 here. So now I have to look for from 2 to 0, from 2 to 1, from 2 to 3, like this. From 2 to 0, is there a direct
Minus
edge
5.
connecting? Yeah.
Yes.
Yes.
From 2 to 1.
No.
1.
No.
No.
From 2 to 1.
No, sir.
So infinite. From 2 to 2. No.
No.
From 2 to 3.
No.
2 to 4.
Yes.
6.
Yes.
Yes. 6. 2 to 5.
No.
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 2 to 6.
Yes.
Yes.
5 is
2
a
to
weight.
6 direct edge 5. So like this. 3 to 0.
No.
No. 3 vertex 3 is here. Now my I got changed. So now I am looking at from vertex 3 to every other vertex. So 3 to 0. No. 3 to 1. No.
No.
3 to 2. No.
No.
3 to 3. No. 3 to 4. No.
No.
3 to 5.
No.
No. Only value will
3
be
to
like
6.
3 to
And
6.
Minus 1.
that is
Right?
minus
And
1.
that is minus 1. Now from 4. From 4, you see from directly from this graph, from 4, only edge is
6.
going to 6.
1, 2, 3, 4 all are nil.
So
Only 6.
0, 1, 2, 3, 4, 5, 6 all are infinites. There are no direct edges.
Except 6.
6.
Except 6. 4
Minus
to 6.
Minus 3.
Yeah, 4
Minus
to
3
6 is
value.
minus.
Weightage.
Similarly, look at 5. Look at 5 here.
Only 1.
Only one edge
5
that
to
is
6.
going
5
to
to
6.
6.
Yeah, so infinite.
And the weightage is 5.
Weight is 5. So look at 6 now.
There
So
is
from
no
6,
No outgoing
There
edges.
is no edge.
no outgoing edge at all. So this will be infinite.
So all will be infinite.
Infinite. Okay. Now this is SP0. SP0 is like we never used any edge in between. We just found the paths between vertex I to vertex J. These are the paths. If I shouldn't have to use any vertex in between, these will be the shortest paths. Yes or no? If I have to go directly without using any edge in any vertex in between, means direct from this vertex to that vertex directly. So these are the shortest paths I can have. SP0 gives me the shortest paths from vertex I to vertex J via no vertices. That means without any vertices in between.
Yes, sir. It is like edge graph with weight labeled
Right.
edge graph, right?
Right. So now SP1. So let's go to the next table, which is SP1. So SP1 actually refers to, now I can use vertex 0 in between. Only vertex 0 in between. Okay. So from the graph you can go, but if you can go from the graph, what is the use of this algorithm? Correct. So by looking at the graph itself, if you can go compute SP1, you can compute SP7 also directly. But there is a connection between SP0 to SP1, SP1 to SP2. So there is a connection. So what is that connection? By looking at SP0 table itself, we can actually compute SP1 table. It may surprise you, but yes, it is true. It can happen. So looking at SP0 table itself, I can actually compute SP1 table. How?
The first row and first column will remain same.
First row and first column will remain same. Okay. So what
Yeah.
will change?
What
No,
will
sir.
change or what will not change here?
Okay, whatever you said is correct. First row and first column will not change. And also we have to look at what will change, right?
Yeah.
What will change?
2 to 5 will be -5 plus -1, so minus
How
6.
how do we get that 2 to 5?
Because from 2 to 5 we have 0 in between.
Don't look at. Okay.
Sir,
So
please,
for understanding
From the start
purpose,
only.
okay,
sir,
for
please
understanding.
complete one row of SP1 so that we can understand that what the SP1 SP2 means.
Okay. So let us first try to look at the graph and try to compute SP1. Then we will understand without using graph how can we compute SP0 to SP1 and SP2. Okay. So that will give you much more clarity. So right now just look at the graph also. Now I have to use. So I am trying to get the SP1 table. Now that means I can use vertex 0 in between. Only vertex 0 in between. So now let's look at this graph now. So if you look at this graph, so what all paths actually can have vertex 0 in between? Only vertex 0 in between.
Only 2 and 5.
Correct. Only this particular path can have in between 0. And no other paths can have vertex, only vertex 0 in between. Yes or no?
Yes, sir.
Yes.
Yes, absolutely, sir.
Yes, sir.
Because only one intermediate step.
So I have to use only 0 in between. 0 vertex in between. No other vertex I am allowed to use.
So everything
like
will
that,
infinity, only these 2 and 5 will be 1.
Now look at from 2 to 5. Look at SP0 value. So from 2 to 5, it is infinite. And now from 2 to 5, the path weight is -6.
-6.
So -5, -1. So which one is the smaller? Minimum. -6 or the infinite?
-6.
-6.
-6 is the minimum. So take that value, minimum value, -6. And rest of the table will be as it is.
Rest of the table will be infinite only, no, sir?
No, it will not be infinite. It will be as it is, whatever SP0 values are.
Oh, so we
Okay, sir.
have to
Means
just
SP
copy the SP0 values. Except this 2 to 5.
So except this value,
okay,
every other thing will be same because there is only one path in our graph.
Okay.
And that also got changed just because the new path got the lesser value.
Okay. If it is more, then we don't have to change that.
We will not change. We are trying to find the shortest path, not the longest paths. Make sure about that. Okay. So if had it been in place of infinite, had it been something else like -8 or something, then it will not change. -6 and -8, the minimum is -8 only. So the same -8 will be carry forwarded here.
Okay, sir. One question, sir. SP1, I thought that it will only via 0. Means
Only via
SP1,
0.
does it mean that via 0 or via or via direct, right?
See, that is what direct or via 0.
Okay. Now I got it. I thought that it is via 0.
Oh, no. So you can use 0 in between. So that is what it means. So either use 0 or don't use 0. Okay. Yeah.
Sir, at this, I mean, the SP, in the case of SP1, we could have choose the node 3. The order we can choose for ourselves, as you said?
No. Once you choose 0, 1, 2, 3, you have to go with numerical order. But this 0, 1, 2, 3, 4, 5, 6, how you fix to these vertices is of your wish.
Oh, yes,
So
sir.
once
That
we
is
fix
what
vertex, then nothing changes.
So once you have assigned one vertex to 0, then that is the 0th vertex. That is the start. Maybe you can treat it like starting vertex.
Yes, sir. Yes, sir. Clear.
So this is just this 0, 1, 2, 3 is like ordering.
Initially, it's our choice. I mean,
initially, see, you give a vertex A as 0 vertex, or you give vertex D as 0 vertex.
okay, sir. Clear.
Okay, it doesn't matter. There it doesn't matter. But once you fixed your order, so 0, 1, 2, 3, 4, 5, 6, once you fix this order, then you are not allowed to change. So that is what we are discussing.
Yes, sir.
Okay. Now, what is SP2 means? I can use two vertices, 0 or 1 in between. Okay. So that means all the paths, direct paths, all the paths which include 0, just 0, all the paths that include just 1, and all the paths that may include 0 and 1 also. Okay. So you have to consider all the paths. So there are 3 cases, all the 4 cases. All the paths include 0, include only 0, and all the paths include only 1, vertex 1, and third one is all the paths include 0 and 1, and final is like direct edges. Okay, not using 0 and 1. Okay, so we have to look for these things. So are there any paths including only 0? The same path which we have seen earlier also.
Yeah.
So you don't need to worry about this. And all the paths including only 1 in between. So are there any paths such that vertex 1 is in between? So no.
No.
No, sir. One
So
doesn't have
the
any
value,
incoming edges.
so the value 2 to 4. Okay.
So there is no edge that is coming to 1, first of all.
Yes.
Yes, sir.
In degree 0.
So just in the same lines, just look at this column of 1. So these are coming
All
towards
are
1.
infinite.
All are infinite. So observe these things also. Okay. All are infinite. So there are no edges that are coming to 1. So that means I cannot get any paths that include only 1. Okay. So this is also not possible. All the paths including 0 and 1. So first of all, 0 and 1 is not connected. So there is no question of asking all the paths that include 0 as well as 1. Okay. So this also will not change, and direct edges we already have from the previous table. So from SP1 to SP2, there is no change. Okay. There is no change just because there are no paths that is having vertex 1 as an intermediate vertex. Okay.
Yes, sir.
That you have to observe. So vertex 1 is not having any incoming edges, or there are no paths that are going through vertex 1. So that is why there will not be any change between SP1 or SP2. So even though I include vertex 1, my shortest paths will not alter, will not change. So that is what we got. So the same table.
We'll carry forward.
We'll carry forward with 6 instead of that infinite, it will be minus 6. So this will be minus 6 as it is. Okay, the table is not changed. So now let's compute SP3. So look at the graph as well as
SP1 and SP2 same.
SP1 and SP2 same. We got it same table. So SP3 means I can use 0, 1, 2. So here also I can look at for the paths that only include 0, only include 1, only include 2, 0, 1, 1, 2, 0, 2 and 0, 1, 2. Okay, you got that right? Only
Yes,
0.
sir. All combinations.
All combinations basically correct. Only 1. Yeah, only 2. Yeah, 3C2. 3C0 plus 3C1 plus 3C2.
Oh, that's
So
2 to the
only
power 3.
Yeah, 0, 1, only 0, 2, only 1, 2 and only 1, 2, 3. Okay, not only 1, 2, 3 and nothing. So there will be 8 possible cases. Okay, all these cases.
So 3 will not be there, no? 1, 2, 3.
Sorry, 0, 1, 2.
0, 1, 2. So here, do we have this order to be considered? 0, 2, 0, 1 instead of 0, 1, can we take 1, 0 or 0, 2 to 2, 0? That
If
way.
there is a path from 0 to 1, then you can consider. It's like if there is a path from 1 to 0, then you can consider like 1 to 0, 0 to 2 like this.
And there is only one direction.
See, now when we compute, you will get to know. Now let us try to understand from graph. Then we will try to understand from SP2 to SP3 how we can come. So right now I can use vertex 0, vertex 1 and vertex 2 as my intermediate vertices now. So now there will be a lot of changes you can see. So using 2, when I can say I can use 2 as my intermediate vertex, then there will be a path from 1 to 6. Then there will be a new path from 1 to 4. And what else?
1 to 0.
1 to 0. There will be a path. And 1 to 5 also. Because you see, the intermediate vertices are 0 and 2 only. So I can use that path. Okay, my intermediate vertices are 2 and 0, which I can use. Now I can use 0, 1, 2, any of the vertices. So I'm using 0 and 2. So there will be a change from 1 to 5. And what else? That's it, I guess. So these many changes will happen right now. So let's see one by one. So initially from 1 to 6, it is infinite. So there are no paths, there is no direct edge, and there is no path via 0, and there is no path via 1, but there is a path via 2 using vertex 2. There is a path from 1 to 6, and the weight of that path is 1 plus 5, which is 6. So now 1 to 6 value will be 6. Okay. Now there is a path from 1 to 4 using 2. So 1
The
to
weight is more, no?
Let's see. So from 1 to 2 and 2 to 4, this particular path weight is 7. Okay. So 1
It
to
will
4.
be easy if you copy the previous values first.
Okay, let's copy them.
Easily comparable then.
Okay, these are the values we have. I will write this -6 also as blue now. So these are the previous values we have. Now what is the value we change from 1 to 6? So from 1 to 6 it is infinite previously, but now I have a path where my intermediate vertex is 2. So I can use 2. So the path weight is 6. So this is 6. Okay.
0
Now,
to 6 will be 4, no?
0 to
6.
Then we are using vertex 5, right? So we are not allowed to use vertex 5 right now.
Okay,
We are only allowed to use in between
0,
0,
1
1,
and
2.
2. Yes, 0, 1 and 2.
So now I can use, there is a path from 1 to 4 and the path weight is 1 plus 6, which is 7. So 1 to 4, look at 1 to 4. Already the path weight we got is 4.
4.
Now the path weight is 7. You have to choose the minimum of it.
Minimum of that
so
is
it will stay as 4.
as 4.
So it will not change. So we are not changing. It will be 4 as it is.
So there is a path from 1 to 4 to 6. So
But then
should
you
we
are
write
using
it?
4, right?
Oh, okay.
See, that is what you shouldn't use any other vertices except 0, 1, 2.
Yeah.
Okay. Now there is a path from 1 to 0 and the path weight is -4. And 1 to 0, initially it is infinite. Now it is -4. The minimum is -4. So we will change it to -4.
And another one is 1 to 5.
And another one we have is 1 to 5.
Initially it was infinite. Now it is in -4, -5.
So it will be -5. So you compute 1 to 2, 2 to 0, 0 to 5. So 1 plus -5 plus -1. So it will be -5. So 1 to 5
is -5.
-5. So you see all the changes happened only in the row 1.
Yes.
And there is no change happened in row 2 or row 0. Correct?
Yes.
And let me just walk you through SP2 now. So right now we have SP2 table as like this, and we are worrying about, I can use 2 now in between, right? These are the shortest paths where I have used 1 and 0. Okay. And 2, 1 coming towards 1, there are no edges. Okay. So that means even if I add some more vertices in between, there will not be any paths going through 1 at all. Okay. So understand that. And one more thing is, now look at the values which got changed basically. So now I can use 0, 1, 2 as intermediate. So look at the columns of 0, 1, 2. So when you look at the columns of 0, 1 and 2, so you look at column 0. So there is an edge from 2 to 5, sorry, 2 to 0. Okay. And you look at rows of 0, 1, 2 also. From 2 to 0, there is an edge, and from 0 to 5, there is an edge. Okay. So you look at this row and this column. And once you look at the non-infinite entries. So that will give you a path through 0. Okay. So here I should have seen it here. So from SP0 to SP1, I can use 0 in between. So if I can use 0 in between, so look at the row 0 and column 0 and look at the non-infinite entries. The non-infinite entries are the paths, basically direct edges. Yes or no? So the only direct edge coming towards 0 is from vertex 2 to 0, and the only edge that is going from 0 is from 0 to 5. Okay, this is -5 and this is -1, and
we have to add those two.
So there will be an edge from there will be a path from 2 to 5. By looking, you can get it by looking these two columns. Okay. Sorry, this row and that column. This column 0 and this row 0. If you look at these two, one row and one column, then you will get all the paths that are going through 0 between using 0 in between. So now from 1 to you look at, so now I have looked at 0. I am done for SP1. Now as for SP1 you have to look the column 1 and the row 1. Okay, once you look like this, now from 1 there is a path to 2, from 1 there is a path to 3, from 1 there is a path to 4, like this. So from 1, okay, and there are, once you see this column and there are no edges that are coming to 1, so there are no edges at all coming towards 1. So that gives you, there are no paths that involve 1 as an intermediate. So then the table will remain as it is. Now for SP2 to SP3, I have to look at the column 2 and the row 2, because see, again you can go back and look at 0, 1, but it will waste your time. 0, 1 we already looked into, well, we already looked at that path. Now you have to look at row 2 and column 2. So look at row 2 first. So once you look at row 2, there are paths from 2 to 0, 2 to 4, 2 to 5, 2 to 6. Okay. And you look at the columns of 2. So once you look at the column of 2, you have only one non-infinite entry which is coming from 1. Okay. So that is why you see all the values in the SP3 table you are seeing. So the paths from vertex 1 will only get changed, or else it will not change. Okay, so there are 4 paths, 4 new paths, and out of those 4 new paths, only 3 got changed and 1 remained as it is. Okay, so from here to here, I have to look into row 3 and column 3. Okay, so this is something like 0, 1, 2, 3 I can use now. Now I can use 3 also as an intermediate. I have to look into row 3 and column 3. So now forget about the graph. Look at row 3 and the column 3. So this is column 3 and this is row 3. So once you look at row 3, there is only one edge which is going to 6. Okay. So once I look at this row, there is only one edge, one non-zero, so non-infinite entry, which is -1. And also look at the column. Once you look at the column also there is only one entry, and that is also coming from 1, and the weight of it is 3. So from SP3 to SP4, the only new path that came is from 1 to 6, and the weight of that path is also only 2. So 3 plus -1, which is 2. So look at 1 to 6. So when you look at 1 to 6, the weight is 6, And by considering the new path weight is 2. So you have to look at the minimum of it. So minimum of it will be 2. Okay. So the only change will happen here, and rest as it is, the table which we have, the table values which we have for SP3, the same will follow, and we will check using the graph now. So we will just go back to the graph. Am I audible? Why everyone are silent?
Yes, sir. We are listening
Yes,
to you.
sir.
Using
Yes, sir, you're audible, sir.
okay.
Yes, sir. We are very dedicatedly listening to you.
Okay. So after looking at the graph, you will get an idea, I guess. Okay. So the only change will happen here, and this will take 2, and all others will remain as it is. So this will remain as -4, this will remain as -5. Okay. Now let's go to graph and analyze. If 3 has been included, what has happened? So now look at the graph now. And once you look at the graph, now I can use 0 in between, 1 in between, 2 in between, 0 1 or 0 2 or 1 2, like this, all these combinations. Along with this, I can use 3, I can use 1 3, I can use 1 2 3, I can use 2 3, 0 3, every other possible combinations. So it's like 2 to the power 4 combinations I will have. So which are 16 possible cases. And out of all those cases, once you look at the graph, what all paths are there which can now include 0, 1, 2 and 3. So I can use, I can have 0, 1, 2, 3 in between.
1 3 6.
1 3 6.
Yeah, 1 3 6 is
3
one
6.
path.
And 1 to 6 is another path.
So 1 2 6, yeah, 1 2 6 is another path.
But it already covered, no?
But it already came. Yeah, it already came. But all the paths I am writing 1 to 4, 1 to 0, and 1 to 0 to 5. Okay. What else we can have as an intermediates? That's it, I guess.
1 2 4 6.
4 we are not supposed to use.
Oh yeah.
We are supposed to use only 0, 1, 2, 3. That's it. So the intermediate, these intermediates should only contain 0, 1, 2, 3. So these are the paths. And if you observe clearly, this path, these 4 paths, we have seen it in the previous table itself. No need to see it again. So the only new path which we have to look is this path. Okay. The same thing we got using the table also. The only path that will alter once I include vertex 3. So including vertex 3 means I have to look into the column 3 and the row 3. And you just compute the corresponding paths. So like this. So look at row 3. Row 3 will give you all the edges that are going from 3. And column 3 will give you all the edges that are coming towards 3. So now if I have to use 3 as an intermediate, I have to look for edges that are coming to 3 and going from 3. So then only I will get the paths that will include 3. And by looking at those paths, if the value changes, I will change the value, or else I will keep as it is. Now from SP4, it is not over yet. Okay. So I will give you a chance to for SP6 or something to compute. SP5 itself I will give you. Okay, now we have to compute SP5 table. Let me bring that SP4 values. So these are the SP4 values which we have. So this is 2, right? Yeah.
2.
Yeah.
2.
So these are the values we have. So in order to get SP5, By SP5 directly. Yeah, SP5. I am allowed to use 0, 1, 2, 3, 4. So 5 vertices I can use as an intermediates now. Okay. So let us, from the graph itself, let us try to get the paths first of all. Then we will go and look at the table. So what all are their paths? New paths now. I need the new paths. Already exist, not the existing paths.
The only
New
new path. Only new path is 5 to 6. Sir.
4, 6.
1,
1, 2, 4, 6.
4, 6.
1, 2, 4, 6 is one path.
1, 4, 6.
1,
1,
4,
4,
6.
6.
Yeah, 1, 4, 6 is another path.
1, 2, 0, 5, 6. 5 is not given.
Yeah, yeah. 2,
1,
4,
3,
6.
6.
4, 6.
1, 3, 6.
1, 3, 6 is already we have seen path, right? Before itself we have seen 1, 3, 6. What else I can use? What else are there? New paths.
That's it.
No, right?
Yes,
These
sir,
are the
these
new
are
paths, right? Now we got 3 new
Sir,
paths.
1, 2, 0, 5, 6.
Then we are using 5, right? As an intermediate. We are only allowed to use 0, 1, 2, 3, 4.
2, 4, 6 will change.
So 2, 4, 6. These are the 3 new paths. Let's
So 1,
compute the
4,
weights
6.
of this
Oh, yes,
one.
sir, that done.
Yeah, 1, 4, 6. It's already there. So let us compute the path weights. So 1, 2, 4, 6. What is the weight? 1, 2, 4, 6. So the weight will be 1, 6
4.
minus 3. So the weight is, total weight is 4. So this is 4. And what is the weight?
1.
1 to 6.
1.
So 4 and minus 3. This is 1. And what is the weight?
3.
6 and minus 3. This is 3. Okay. So for our, from the graph, we got that. So you look at 1 to 6. So 1 to 6, we already have path weight as 2.
Yes, sir.
Okay. So
Which
1
is
to 6,
minimum.
we have 2 new paths with weights 4 and 1. Out of them, minimum is 1. And 2 and 1, what is the minimum? It will be 1. Correct?
Yes, sir, 1 will be there.
6 will become.
Sir,
So
1 to 6, there is 1 is minimum, no?
1 is minimum. So for, see, from the graph, what we got is this value should be changed. Correct? This should be changed.
Yes, sir.
This should be 1. And from, there is one more path from 2 to 6 also. So let's look at 2 to 6. 2 to 6, the weight is 5 initially. Now here the weight is 3. So this one also should be.
Sir, 1 to 6 is already the lower, the value is lower than the recent one.
No,
Because
this
4
also, this all. So there is a path from 1 to 6. There are 2 new paths from 1 to 6 now. And out of them, the minimum is 1 here.
Okay.
So the path from 1 to 4, 4 to 6 is the minimum. Not the path from 1 to 3 to 3 to 6. Okay.
Sure.
Okay. From the graph, we got that these two values should be changed. Okay. So from the graph perspective, everyone got it?
Yes, sir. What about without graph
With the
now?
table, let's see with the table. Now I am looking at the SP5 table. So for SP5 table, I have to look
Row 4.
4. So actually in SP4 table, I have to look the row 4. So let me go back to SP4 table. In the SP4 table, I have to look at row 4 and the column 4. So once I look at the row 4, the only non-infinite entry is minus 3. So there is a path from 4 to 6 and the weight is minus 3. And look at the column 4. When I look at the column 4, there are 2 entries.
2 to 4
1 and 2
and 4 to 6.
Okay.
with weight 4 and 6.
With weights 4 and 6. So now from this particular table, I got two paths, two altering paths from 1 to 6 and from 2 to 6. So from 1 to 6, the weight is 1. So if I compute the weight is 1. So here it is 2. So the weight should be changed to 1 from 1 to 6. And also from 2 to 6, this particular new weight is 3. And initially 2 to 6, the weight is 5. So this particular value and this particular value should be changed from this particular table. So directly go to SP5 table. This value should be changed to 1. And this value should be changed to 3. So from the table or from the graph, we got the same thing. Okay. Now understood how you can come from one table, one SP table to another SP table?
Yes, sir. Yes, sir. Now we understood.
Yes, sir. It's clear now.
And now it's
compute,
easy to calculate from the tables.
From the table, it will be easy. So that is what I
Yeah.
wanted to emphasize more. From the table, you just have to look rows and columns. That's it. So you didn't even get this particular path, you see.
So
from the
technically,
graph,
we just want just one SP table, that is SP0.
SP0.
Other
That's it.
tables we can derive from that.
From the table itself, you can derive. That is what. That is why this algorithm.
Yes, sir.
You can use this algorithm. So for see here, the graph is only 6 vertices. Okay. What if the graph has some maybe 70, 100 vertices? Can we look into all the vertices and compute the shortest paths, all the paths, and out of those paths, computing the shortest path will be very, very difficult.
Yeah, very tedious as well.
Tedious as well. So
Now
even
the
though
value
your
of this
graph has,
algorithm is revealed to us.
so even though your graph has 100 vertices, you will have 100 cross 100 table, but you have to look into only one row and one column. So it is more of like some out of 100 square values, you just have to look at 100, 200 values, not even 200, 199 values. That's it. So 199 is far, far less than 100 square. Correct?
Yes,
sir.
Yes, sir. And the calculation is lesser from the digest.
Lesser. So you will not get these kind of paths. So this path is useless path to find.
Yes,
Yes, sir.
Correct. From the graph we got it, but anyway the weight is higher. So you don't need to get this path at all. So from here you will get it directly. So now in order to compute SP6 table, I can use 0, 1, 2, 3, 4, 5 as my intermediate vertices. But I just have to look at row 5 and column 5. Just tell me what all the changes will happen from SP5 to SP6. I will give you graph also.
Sir, I just computed, sir. And,
Just wait for 30 seconds. Okay. Let others also try. So
yes,
don't use the graph. Just try to come from SP5 to SP6. Okay, I will give you the hint also, those who are struggling still. So look at row 5 and look at column 5 now. Okay, from looking row 5 and column 5, you get the paths. Yeah, so shall we discuss?
1 to 2 is 1.
So let's look at row 5 first. Okay, so once I look at row 5, I have only one non-infinite entry, which is
It's 5 to 6.
5 to 6.
With weight 5.
And weight is 5. And then I have to look at column 5.
Incoming.
Yeah.
0
So
to
once I
5.
look at the column 5, there are 3 non-infinite entries. So which is from 0 to 5,
1
to 5,
1 to 5,
2 to 5.
and the
2 to
weightage
5.
is -1, -5, and -6.
Yeah, -1, -5, and -6. So now I will get a path from 0 to 6
With weight 4.
with weight 4.
4.
So I will get path from 0 to 6 with weight
+4.
With the weight +4.
1,
Yeah,
2.
+4.
Correct. So look at
Yeah.
0 to 6. So look at
So
0 to 6 in the SP5 table.
It's
It is
infinite.
infinite.
2 to
So
5.
infinite and +4, which is minimum?
+4.
+4. So this will change.
-1.
Okay. So this will change. And just this is done. So let then go to next path.
1
So
to
1
6.
to 5, 5 to 6. So there is a path from 1 to 6 with weight 0. So -5 +
Previously
5.
it was 1.
So previously it was 1. So 0 and 1 minimum is 0. So this will also get
2
changed.
to 6.
Now from 2 to 6, the weight
-1.
I'm going to get is -1 here. But from 2 to 6, if you see here, it is 3. So -1 and 3, minimum is -1. So this will also change. And only these 3 values will change and rest will be as it is.
6. 6.
So those who are looking from the graph, you should get this.
2 to 6 is 2 to 6 will be -2.
Okay. So even though you do it from the graph, you see now I can include 5 in between. So I can use 0, 1, except 6, I can use all the vertices now. So I will get all the paths that have intermediate vertices as 0, 1, 2, 3, 4, 5. So once if I include 0 as my intermediate vertex, now the new paths will be like 2, 0, 5, 6. So this is one path. 0, 5, 6 is another path. And from 1 to 2, 2 to 0, 0 to 5, 5 to 6 is another path. 1 to 2, 2 to 0, 0 to 5, and 5 to 6 is another path. So these are the 3 paths which we are going to have. And you compute the path weights, you will get this. Okay, from there also you can do, from here also you can do. So one more thing is why we are only looking at row 5 or one particular row and one particular column is because till SP5 table, the values which we are seeing in this, you are seeing in this particular row, this value is actually the shortest path that is coming towards 5 from 1. Okay, this -5 will give you the shortest path from vertex 1 to vertex 5. So it may come from in between my 2 or 3. It may have intermediate vertices also, but the shortest path from 1 to 5 is -5 till here. So that means whatever the edges that are edges coming towards 5. Jigisha, can you mute?
Oh yes, sorry. Sorry.
Yeah. Thanks. So you look at, so whatever the values you are seeing, those are the shortest paths already till 5. And whatever the row you see, it's from 5. And combining, you will get the shortest paths including 5. That's it. So slowly we are including one vertex into our table and we are finding the shortest paths. So this is what Floyd-Warshall algorithm is doing.
So
Okay, now
it
got
means
the
we have not used 5, the vertex 5, and we have used all other vertex.
previously we
Previously
didn't
1 to
use
4 vertex.
vertex 5 and vertex 6, and
0
we have
to
used
4.
If I do
0 to 4 we have used to reach 6. Now we are calculating also along with 5 and checking whether they are coming minimum or not.
So now finally we have to compute SP7, which is including all the vertices. So now I can include 6 also in between. But if you see for SP7, if I have to include 6, I have to look at the row 6. And if you look at the row 6, there is no
outgoing edges, sir.
No outgoing edges at all. So even though I include 6 as my intermediate vertex, there are no paths that will have 6 as an intermediate vertex. So even if I
So
look
it
at
will just
SP7 table also, it will not change. SP7 table and SP6 table both are
it will
same.
replicate.
It will be same. So now what we get finally is the shortest path, whatever the values you see in the final table, SP7 table. Those are the shortest paths from one vertex to other vertex. So now this
SP6
is
SP6 represents shortest path.
This will be SP7 only. SP7 will give you the shortest path.
Okay. Here SP6, SP7 same, but
This is
SP7 gives.
SP7. So including all the vertices will give you the shortest path. So SP6 only you have included 0, 1, 2, 3, 4, 5 only. Still 6 is remaining. So if you have to include 6 also, then you have to compute SP7 table. Okay. So SP7 table.
One task of finding shortest path is done.
So what is one for?
There is one more application. No, you have said cycle, negative cycle.
For negative cycle, if there is a negative cycle, if I include, if I try to find, what we can say?
SP8.
What is SP8? I didn't understand. I just said initially, but I think via Floyd-Warshall it will be a little difficult to get the negative cycles. Via Bellman-Ford we can get negative cycles. So let me check on this, okay? So let me check on this. Can we use Floyd-Warshall to get negative cycles or not?
Okay, sir.
Okay. Yeah, I'm
Bellman we will study.
Bit not sure. Bellman-Ford yesterday, I heard yesterday they have discussed Bellman-Ford.
Okay, sir.
Okay. So this is SP7 and SP7 will give you the shortest path you can check. So this is the SP7, you can check anything you take any value, -3. So if you take -3, this -3 is the shortest path from vertex 4 to vertex 6. See from vertex 4 to vertex 6. This is the direct edge that is connecting vertex 4 to vertex 6, which is -3, and this is the shortest path. And you see this 0, 1 to 6, 0. So 1 to 6, there is a path with weight 0. So you see in the graph there are many paths that go from 1 to 6. This is a path. This will be a path. This is a path, and this is one more path. And finally, this is another path. Out of all these paths, you see this 1, 2, 0, 5, 6. So this path has weight 1 minus 5 minus 1 plus 5. So the weight of this path is 0. So all other paths will have greater than 0 weight. And this is the shortest path from 1 to 6. So like this, you can get shortest path from any vertex to any other vertex. Okay. And this is how you will use Floyd-Warshall algorithm to compute these tables. And from one table to another table, just look at that particular row and that particular column and identify the new paths and change the values accordingly if they are minimum, or just don't change if it gives you the maximum. Okay. Fine.
Yes, sir.
Yes, sir.
So the book you recommended, there is no algorithm, is there?
There are, right? Applications.
Which book recommendation?
I just downloaded the book.
Graph theory with applications. Bondi and Murthy. You ask me the applications or algorithms?
Algorithms, sir.
Algorithms they have discussed. Just look at the application pages. They have discussed few algorithms.
Okay.
And see, for this Bondi and Murthy, it's more of like, you see, it will be useful for you to go through the week 10 contents rather than these algorithms. They will not discuss much in detail. Rather, you use if you know the electrical graph theory books, there the algorithms are much more in detail. So I will just try to get one more book. Okay, if I got any book, then I will post it in discourse or discussion forum. Okay.
Yes, sir.
Okay. So I will not discuss longest path also. Longest path is also okay to go, but transitive closure I just wanted to highlight. How many of you know this
PDF
transitive
you have
closure?
provided, sir, right? Are you saying?
Which one?
The book, the recently you mentioned Bond.
No. This is not the recommended book. So what we recommend is to go through the lectures only. Madhavan sir's
No, actually,
suggestion is
is it present in portal?
No, it's not present on the portal. You have to download it via online sources.
Okay.
How many of you don't know what is transitive closure? No one, is it? Okay,
We
then.
know,
Okay.
We have to calculate A matrix A square and we have to add them up.
You have to add them all.
Up to n
okay.
minus 1.
That is one way. Okay. Then in that case, let's try to answer this question. So let me just zoom out. So how many edges will be there in the transitive closure of the below given graph? Okay. So this is the graph. And if I wanted to compute, if I have computed the transitive closure of this graph, then how many edges will there be in my transitive closure graph? So everyone please try this.
One idea is to calculate a big matrix.
Okay, one idea. See, try to compute. We have 10 more minutes. We can discuss this and we will end the session. But in general, how is graph theory? Is it interesting or boring?
Interesting, sir.
Interesting, but taking too much time.
Yeah, time taking.
See, even though it takes time, if you are interested to spend time, then that is okay.
I think if we spend enough time, the question will not be tough after that. Means every question will be solvable, right?
Initially, it will take time.
Initially, it will take time, even I agree. But which one is good, calculus or graph theory?
Graph theory, sir.
In toughness, graph theory is better.
No, in interests and everything. So when you look at week 7, week 8 contents, if you wanted
Calculus
to
is
open
little
the
more
portal,
interesting because we can do a lot of things. We can find derivative. We can find maximum value, minimum value.
So tell me one thing, How many times did you open the portal when calculus part is going, and how many times you are interested to open portal when graph theory weeks are going?
Every time we open the portal, sir.
Every
We
time
have
you
watched
open portal, but with interest, without interest. My question is, Arey yaar, now I have to open the portal and I have to look into the contents.
Graph
Or
theory,
graph
very
theory, sir.
interestingly open.
Because this is, I think, first interest.
New topic also.
Yeah. So practice more problems in graph theory. So in NDEM, we will definitely focus more on graph theory and week 9 of
week 12 is division session only, no?
Yeah, week 12 we will give you some 4 or 5 videos which we recorded. So
Revisions.
Revisions, complete revisions of, not complete revisions, the more difficult concepts. Maybe in one video we have revised all the relations.
So in final exam, what will be the weightage is like? I mean, the week
That
wise.
you will get to know. So maybe in the later weeks you will get to know.
Okay,
so there
sir.
will not. We will give the questions from week 1, week 2 also, but the weightage will be slightly different. Maybe you can treat it like 33% till week 8, not week 8, week 6, where this logarithm end. So 33% will come from that, and 33 from calculus, and 33% from graph theory.
Okay,
Like this it will. Okay. So if there are 12 questions in your question paper, NTEM question paper, then definitely 4 questions will be from graph theory, 4 will be from calculus, and 4 will be from weeks 1 to 6. Okay. So like this it will be. Yeah, tell me, what is the answer to this question?
Sir, matrix I'm not made yet.
15, I think.
15 is one answer. Option A is 15. Any other answers? Okay. So instead of using matrices, can I directly compute transitive closure using the graph itself?
Yes, sir.
Yes. Okay. What is transitive closure means? First of all, it's basically in a particular graph, if there is a path from vertex u to vertex v, then we add a direct edge from vertex u to vertex v. That's all. Okay. And
Yes, sir.
we will keep this adding edges, and after adding all the direct edges, the newly formed graph is nothing but the transitive closure of the previous graph. So if the graph is like this, so what I have to do, I have to add edges between two vertices if there is a path from that vertex to the other vertex.
Sorry, is it G complement? You have G and above bar.
It's G bar. So sometimes it's referred to complement also, but sometimes in this particular notation we use G bar. I just use G bar. That's it. So the newly formed graph G bar is called the transitive closure.
G bar or G plus?
G plus is also okay. So let's use to your notations only. G plus. Okay, this is the denotation. Okay. Okay. Now what I have to do, I have to add, keep on add edges, direct edges. So look at the paths. So I have a path from 2 to 4. So I have to add an edge from 2 to 4. Okay. And also from 2 to 3, I have a path. I will add an edge. And what else? From 2 to 0, there is a path. 2 to 1, there is a path. So I will add an edge. So like this, I will add edges. And what else are there? That's it, I guess. 2
So
to 3,
2 to 1, where is for 2 to 0 and 0 to
2 to 0 and 0 to 1.
Okay.
Okay. So I guess these are the paths. Okay. 4 to 3, 3 to 1, there is a path. So there will be a direct edge from 4 to 1. Okay. And I think that those are the paths we are going to get. That is it. So these are, so once after adding all the direct edges, so this is the newly formed graph, which is the transitive closure of this previous graph. So similarly, here also I have to do the same thing. So look at the paths. So I have path from B to I. So I will have a direct edge. B to H, there is a path this side, and
B to G.
B to F,
G as well.
B to G as well,
B to A.
A,
J
B
also.
J,
B to A, B
B
to
to
J.
J.
Okay, so we are done with B. So like this, D to F,
D to G.
D to G.
C to J.
No, first let's complete D. Okay.
D to A.
D to A. How?
No, nothing. Nothing more.
D is done. Now C.
D to F, how?
D to F is how D to H and H to F. There is a path.
Okay. Yeah.
So from C to J.
C to F.
C to J, C to F,
C to G.
C
C
to G.
to G,
C to I. No.
C to no I.
No.
That's it. And from E to F, E to F because E to H and
So is there.
C to J, what is path?
Also there.
Sir, C to J, how, sir? How?
C
C
to J,
to
sir,
J,
how?
J to
C
H,
to A and A to J.
F to.
Oh, yeah.
C to A and
Yeah,
A to
it
J,
also.
C to J. Okay, so like this. So finally H to G and J to G. J to G is because J to H and H to F, F to G. J to G, and you see
A
from
to F also.
A to G. So A to F there is an edge. So A to G.
J to F is also there.
J to F also. So like this you have to add all the edges, direct edges, if there is a path from one vertex to other vertex. So now after adding that, this can be the question. So how many edges will be there in the transitive closure of the below given graph? So all the black edges. So black edges plus red edges is equal to the number of edges.
Edges are 15.
Which edges? Red edges or complete? So
Black edges are 15.
Okay, black edges itself is 15, is it?
Hmm.
Okay, black are 15. 15 plus red. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14,
6, 7,
15,
8,
16, 17.
17.
17. So 15 plus 17, you are going to get 32 edges as the answer. So add under 32 as the answer. Okay. So first of all, in graph theory, know the concept clearly. Then try to solve as many problems as possible in that particular concept. And definitely it will be easier for you to solve the later question.
So this is the only way. And matrix.
Matrix is one more way. See, here the graph is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices. Okay. If the graph is like if the graph is like some 50 vertices, we can't keep looking at the graph and add all the direct edges, right? So that is why, so if you have the graph, then you will definitely have the adjacency matrix. Once you have the adjacency matrix A, you can compute A square, A cube, A for 4 like this till A to the power n minus 1.
49.
To A to the power 49. and you add all a plus a square.
It can
plus
be
a
done
square.
by computer only.
It will be done by computer. So you
And
don't need to
otherwise,
worry.
we have to draw like this.
Yeah. So
We
in
have to fill up.
examinations, most probably you can use both the methods. If you are able to compute matrices also, it's fine. Or just directly draw the graph also, it's fine, because we will not be going beyond 10 vertices. Okay. So whatever the graph you see, it will be easy graphs, smaller graphs. Okay.
So I think this type of video are covered in tutorials, right?
No, week 11 tutorials. Is that tutorials in week
No,
11?
sir, there is no tutorial in week 11.
No. We don't have tutorials in week 11, but we had tutorials in week 10, I guess.
Define current atlas.
Okay, then that's it for today. And we
So
have one
please
more session
share the
on Thursday
slides.
morning. Yeah, I will share this slide.
One more session.
So
Yes,
one more
sir, one
session
more
is there
session.
on Thursday morning.
Okay.
There we will discuss this minimum cost spanning tree and Prim's algorithm, Kruskal's algorithm, and everything.
And assignment dates are very near.
Yeah. Assignment date we will try to push it to Saturday or Sunday.
Okay,
Sunday
sir.
there is OPP exams, I guess. So maybe we will push it to Saturday, or maybe we will push it to Monday.
But OPP for us or for second semester students?
Yeah, but few people, are there no common people? Is it Max 1 and Python? See, those who have done CT earlier, they can take Python, right? Python and Max 1 at the same time.
But maximum 4 subject we could take, no, sir.
Maximum?
We are first term student. Maximum 4 subjects are allowed.
Yeah.
No?
See, you are first term student. There might be few students who are second or third term. They have taken Max 1.
Okay, for them.
So for them, there will be a
OPP.
clash.
Okay.
So the fraction is very less, but we should also consider that fraction into the picture, right?
Absolutely, sir.
Yeah. So okay then. Thanks for joining and have a good day.
Thank you, sir.
Thank you, sir.
Thank you so very much, sir.
Thank you, sir.
Thank you, sir.
Bye.
Thank you, sir.